Okay, I guess so we can get started. Probably a few people will be coming in a bit late. Okay, so I'm going to start on the last topic for this course, which is information theory, and we have just about 2 weeks to cover it. As with all the other topics in this course, it's a very deep topic. It has a lot of important, difficult, interesting ideas in it. And my goal here is to try and get you to a stage of being able to at least understand or appreciate some of the more advanced work here. So it's still very elementary and a basic idea, and I'm going to try and focus on the intuition. And again, I should point out that I'm not an expert in this area, so the perspective I'm bringing here is somebody who's learning it, I just learned it a few months ago, and so hopefully, it's understandable because I tried my best to understand it. Okay, so information theory grew almost completely from just one piece of work, which is kind of interesting. Just like game theory, which also almost grew from just one paper and one book, information theory, almost all of it grew from one master's thesis by Claude Shannon, who wrote his thesis at MIT, I think in 1940 something, 47, 48, something like that. And I mean, remarkable piece of work, for a master's thesis. So can you imagine your master's thesis starting a whole theory, and then 50 years later or 60 years later, there are over 100 conferences and many thousands of people, and the entire information revolution. Pretty much you can say everything having to do with computation and communication, networking, computers. All of it depends on information theory to some extent. So it all came from one master's thesis, so it's quite nice. And really this whole chapter, all it is trying to give you some sense of what the thesis does. So the end of the chapter, which is the kind of a sketch of Shannon's proof of capacity of a noisy channel. The proof is actually the thesis, and that set the basis for really all the work that's happened subsequently. Anyway, so the purpose of information theory, that what Shannon started out with, was to figure out what does it mean to communicate, okay? And he had some very practical concerns, but he was a mathematician. He was a very good mathematician, but he wanted to find a model for communication. And so for him, communication was a very broad thing. So you could say communication happens, I'm talking to you, obviously I'm communicating. But if you walk past a billboard and the billboard has some advertising message in it, you could say, well, that's communication as well. The billboard is communicating something to you and to every passerby. And if you listen to something on the radio, that's communication. If you listen to something on TV, that's communication. You get email, that's communication. So clearly, there's a lot of communicating going on. Okay, every day, you're exposed to a lot of communication. Is there something that's common to it? Is there something that unifies it? Because if we can find this unifying theme, then it would be possible for us to model it. And then by modeling it, we can analyze it mathematically. Okay, so we have this whole process, and this is the process of how kind of science advances. We take an area which looks very diverse. Okay, it doesn't look like there's any structure to it, and if you go deeper and deeper and deeper, hopefully you find a point at which there is structure and there is a model, and the model is really our mathematical way of representing what is unifying to it. And this is what we do, right? So when people want to study brain, for example, we think of the brain or the mind as being something we don't quite know. And today what people are doing, with the frontiers of science, is to take that and to find some structure, some model for it, and then we can use that model to understand what's going on. Okay, so for example, memory formation. Okay, what is it that causes memories to form? Okay, so the goal of this lecture, or goal of any learning, is for memories to form, right? As I said in the beginning of this class, what I'm doing here is practical brain plasticity. I'm trying to change the inside of your brains, okay? And so are you. You're trying to collaborate with me, hopefully, to change the inside of what your brain looks like. What's going on? We don't know. We just know that if I talk at you and I draw stuff on this board, somehow your brain changes its internal configuration, and then later on when I have a test, you can say, oh, I know this. Okay, so So we don't quite know what's going on actually, okay? And it's possible that in the future you just, you know, take a cord, plug it into your brain and plug it into some machine, and then you program yourself to know information theory and you're done. I mean, there's no need to go to university, okay? It's kind of, you can just spend your time, you know, going to a bar and, you know, having a lot of beer, because that's the other part of university that we can't provide, but we can just plug it in and turn and flip a few switches and we program your brain, you know, the direct method. So anyway, to come back to this, what Shannon did was to say that the basic model for communication is that there's some source, obviously, which is sending the message, and there's some recipient. And connecting the two, we think of it as something called a channel. And for now, we'll say the channel is unidirectional. And on this channel, we have a message. And those are the four components of any communication system. There's got to be some source. So if you think of a billboard, the source is the billboard, you're walking past it. The channel is, I guess, the billboard itself, or the air between you and the billboard, and the message is what's written on it, right? If you listen to radio, the source is the radio transmitter, you're the radio receiver, and the channel is the RF radio frequency medium, and the message, whatever is being sent, and so on. So we can always take any communication and break it up into these four pieces. And given this, now we can say, okay, we found the basic building blocks of a communication system, and now we can say, okay, we can start modeling it. Okay, so in the same way, we don't actually have the building blocks for memory formation yet. Okay, because we have some sensory input, we have some internal input, and then we know it's stored in the hippocampus for long-term memory, but we don't have all the bits and pieces. We don't even know what's involved in it. For communication, we do. Okay, the recipient and the channel are not so obvious actually. For example, I might take a CD and I listen to some music, for example, burn it on the CD. There's no recipient actually. The recipient is actually putting it on the CD, right? The source is some audio source, and the channel, I guess, is whatever it takes to listen to the audio, the microphone, and then the digitization, and then the recipient here's a CD. So it can be a bit non-trivial, but anyway, we'll work with this for now. So everything in this chapter concerns this basic model over here. Okay, source, channel, recipient, and the channel can be complicated. The channel can be bidirectional, for example, or the channel can be multicast, which means it goes to more than one recipient, or it could be broadcast, in which case the source sends out something and a whole bunch of people receive it. Okay, everybody who's in range receives it, which is what we do with Wi-Fi. So the Wi-Fi transmission, radio frequency, we have omnidirectional antenna, you put some message out, everybody receives it. Okay, so, but again, for the purpose of simplicity, we'll study a single unidirectional channel with single recipient, so that life is as simple as possible. Then the next question one could ask, the next question Shannon asked was, okay, what does it mean to communicate? You know, what does it mean precisely to say that a message has been exchanged? Okay, for example, you could imagine the source sending a message, but the recipient didn't get it, got lost. Okay, or the recipient didn't understand it because of a different language, right? You could see a big sign that says danger, if you cross this you're going to fall off the edge of a cliff, but the recipient, you couldn't understand the sign, you just fall off the edge of the cliff. Well, communication did not happen. So at some level, what we're saying at communication happens if and only if the information state of the recipient changes. So we can think now of the recipient being in a particular state, and a message arrives. At the arrival of the message causes the recipient to go to a different state. Okay, so this change in state of the recipient we will call communication. So if the recipient does not change state, then we say that no communication happened. Okay, so now we're getting a little bit more grasp on this nebulous concept of communication. So if somebody talks to you, didn't understand them, communication did not happen, right? Needs to be. So the recipient has to change its state, so it has to go from some state, original state, to the new state, and we'll attribute this to the communication. Okay, that's the meaning of communication. So the difference between the original and the new state we will call the information content. Okay, so this difference is the content. So what we're saying is that the effect of the message is to convert the information content of the message, is to convert the recipient from some original state to some new state. Okay, and that is now becomes a bit more precise of what this is. Okay, so we come down to a slightly simpler problem. Instead of modeling the whole source, message channel, etc., we're going to model a bit simpler problem, which is that what is the change in state of the recipient? Okay, we can forget about all this stuff. You can just forget it. We just focus on what is the change in state of the recipient. What does it know more? Okay, and so again, we're going to restrict our ideas further and further, and we're going to take a very, very simple example. Let us say the source. Okay, let's say the source knows can send one of 16 messages. Okay, one of 16. It can send one of 16 messages, and we'll just number them 0 through 15. Okay. And the recipient is sitting over here, and the recipient knows that source can send one of 16 messages. So remember, this is a fairly important simplification. Okay, typically, if you're walking past a billboard, you don't know what's going to be on the billboard. So it's not like you know, right? You don't know. But here, for the sake of very simplifying analysis, the recipient knows that the source is going to send one of 16 messages, and again, for the moment, we'll assume that the messages are equally probable. Okay, they're all equally likely. We don't know. So think of it like so you're sitting behind a screen. A source picks a number out of from 0 through 15 and says 7, and you say, "Aha, okay, I did not know it was 7. Now I know it's 7." Okay, next message, I don't know what it is. The source picks 4. Okay, now the recipient knows it's 4. So this is, one could argue, the most elementary form of communication. Okay, we kind of restricted it down to such a small thing that we can now actually analyze it mathematically. Okay, and so the source is going to send one of these 16 messages. Recipient doesn't know what it is. Source picks a message at random, equally likely. Okay, and says, I pick a number, recipient. We can now say this is exactly what the information content is. Originally, it didn't know. Now it knows. Okay, which of these 16 messages were picked, and for good reasons, which will become clear in a bit, we'll say that the information content is the logarithm of the number of messages. Okay, in this case, this was going to be 4. It's always base 2, so it's going to be 4. Okay, so basically what you're saying is that we'll actually now give a numeric value to the information content as the logarithm of the number of equiprobable messages, okay, which kind of went away. That the uncertainty in which of those messages collapsed, and we just got, that's got that one thing, and we say at this point the recipient has the information content of 4 somethings. Okay, and now we can quantify. We have quantified the communication path. Instead of saying that some source, some message, some recipient, we can now say when these conditions hold, okay, and it sends a message like this, the information content from the old, it was 0, and now the new state is it has 4 somethings, okay, where 4 is defined to be log of the number of possible messages, equiprobable messages, and the unit that we use is a bit, and this is called 4 bits. Okay, and so the bit is a sort of contraction of the word binary digit. Okay, and in a minute you'll see why it's called a bit. But okay, I'm going to stop. So, are there any questions about this over here so far? Okay, so you read all this. I'm trying to kind of give you the intuitive understanding of what's going on. So we've taken a very, very restricted scope in order to make this manageable. Okay. Okay, any questions here? Okay. So, in computer science, and generally speaking, we get accustomed to bits. We think of bits and kilobits and megabits and gigabits and terabits. We don't pause to think, where is it coming from? Where did that word bit come from historically? But more importantly, what's the information content? Okay, what is associated with this? To just give a perspective on this, let's start with this here and say 4 bits. What we're saying over here is that one way of interpreting this is that is the following. Let us say that the source can send 16 messages, it can send one of 32 messages. Okay, all right. Now, if it can send one of 32 messages, one could argue that we could divide it up into 2 bundles of 16 messages each. Okay, like so. And then what will happen is that it first tells the recipient, okay, let's call these bundles A or B, or we can call them 0 or 1, okay, it doesn't really matter. And the first thing it tells the recipient is, I'm going to send you a message that belongs to bundle 0. Okay, we don't care what's in these bundles, as long as they're all equally probable, I don't really care. So I'm going to send you a message 0, and the recipient gets this and says, aha, at this point I know that it's going to be one of the messages in bundle 0. And then it's going to send me something from bundle 0. I don't know what it is, okay? So, and then that's going to cause my information state to go up by 4, okay? One could argue that then the total amount of information the recipient got is 5 bits, okay? The first one tells it which bundle, and the second one tells it which message inside the bundle, okay? So, by recursion, you can see that I could actually break up the 16 into 2 bundles of 8, etc., and these into bundles of 4, etc. So what we can think of is this actually a binary tree. Okay, there's a binary tree which is starting from the root and going off to each of these 32 messages, and each symbol that is being sent, or each message that is being sent over here, tells the recipient which path is being taken in the binary tree. And so we can think of each binary choice as corresponding to 1 bit of information. Okay, so we have a tree that looks like this. Okay, for example, this is a tree of, so we're going through this binary tree, all paths are equally likely. So we can think of the actual message as being some path in this tree like this. Okay, and so I've taken one decision here, and then over here I know which one it is. So I'm taking one decision here, one decision here, one decision here. I take 3 decisions, and when I have 3 decisions sent to you, then the recipient is going to know exactly which message was sent. These are the, in this case, 8 messages that are being chosen over here. So if we have 8 equiprobable messages, one can now mathematically state that the logarithm of 8 must be the information content associated with it. That's why I use the logarithm. Okay. So one of the confusions or questions people have is why log? Okay, this is why it's log. This is why for entropy we use log, and we'll come to entropy in a minute. But this is because we are viewing the set of all messages as being ordered in some kind of binary tree. Okay, not a ternary tree, a binary tree. And over here we are choosing this path, and so you can see this example of going 16 to 32 gives you the intuition right away that each doubling of the number of messages is actually adding only 1 bit of content, because you can always partition it into groups and then we can send it off. Okay, so we get the nice result that if we have a set of n equiprobable messages, keep mentioning equiprobable, because in a minute I'll take that away. If you have n equiprobable messages, then we say the information content. The information content that is communicated to the recipient on sending one of these messages, okay, is going to be given by log of n. So the funny thing is that we don't really care what the messages are. You know, these messages could be anything. It could be novel. There could be 16 different, novels. It could be 16 pictures. It could be 16 movies. It could be 16 or 32, whatever. We don't care what the actual content is. We know but we need to have the recipient knows that can send one of these 16 messages. It's important that the recipient knows that. Okay, so we can think of the set of possible messages as already with the recipient. It already has it. Okay, it just doesn't know which one. Okay, that's the model we are putting over here into place. So it's not like I'm sending you the actual message. I'm just telling you which one to pick out of the set that you already have. Okay. So it's like you're sitting at home, you have, some 10,000 songs in your iPod, and your friend calls you and says, oh, I want you to play song number 2356. Okay, that's the information content. It's not the actual content thing. So then you say, okay, if I have 10,000 possible songs, then log 10,000 is the information content of the message that's sent to you. Okay, so it's a very interesting and different context of communication, but that's what we start with over here. Okay, so that's sort of the first step in this path where we say, if you have n equiprobable messages, the information content is log m, and we give it the name entropy. That's now Claude Shannon chose this word to relate to the chemical notion of chemistry, entropy, or it's also used in physics, the notion of entropy. So it was a deliberate choice. It's sometimes confusing, but in this particular case, all we mean in entropy is essentially what's the information content of that was communicated. Okay, and so we say that the entropy. The other way of putting it is that the source has an entropy of, in this case, 16 messages. Source has some entropy of 4 bits. And it sends a message, and the entropy of the message is 4 bits, and the recipient now gets 4 bits of entropy. Okay, we'll clarify entropy in just a minute, but basically the entropy corresponds to a set of messages. If you're given a set of messages, okay, then I can tell you the entropy corresponding to the set of messages. Okay, so entropy. So it's a communication model, content entropy. So we're going to look a little bit more into entropy. So entropy is always denoted using the symbol H, and entropy is viewed as the the information content of a set of messages. So just a moment, just a kind of a footnote. The notion of entropy was introduced in chemistry, okay, and the entropy in chemistry, I guess in thermodynamics, refers to the amount of disorder that is present in a system. So if you have a system that's totally ordered, then that system has 0 entropy, and it gets more and more disordered, you have more and more entropy. And when it is in a state of maximal disorder, we call it the highest entropy state. So just for the sake of illustration, this room has a certain number of air molecules in it, which are distributed in some fashion. You can't see them, but they're there. Let's say all the air molecules decided to go sit at that corner over there. Well, you'd all asphyxiate, okay, to begin with. But that corner, having all the air molecules in one corner would be a state of minimal entropy. Okay, the entropy would basically be 0. It will be maximally ordered because it's all in one place. And if it spreads out and moves all over the place, the entropy is greater, and so there's more disorder. And the second law of thermodynamics tells us that in any real system, entropy is going to increase. Okay, the second law of thermodynamics basically says entropy constantly increases over time, and so that rules out things like perpetual motion machines, because in those machines, entropy does not actually increase. Anyway, there are some various myths about entropy that I won't go into. I'll note just here that here we view disorder as being, in some sense, having more information. Okay, because if all the air molecules are up in that corner over there, I don't need any information to describe it. I can just say, yeah, we are in this room, all the molecules are there. It's a very compact description of all the molecules, all in one place. Right? No, you can just say, here are the coordinates, this is where all the molecules are, we're done, right? You just have to send a small message. But if the molecules are dispersed all over the place, I need to say, yeah, molecule number 1 is here, molecule 2 is there, molecule 3 is here, etc. So there's more disorder, okay? To take a more practical example. Let's say that I have a square like this, and in this square it's an image that I want to send, okay? And let's say that I have some stripes, so black and white. So, I just have, let's say, 3 stripes, and these are white stripes, and the rest are black, for example. Then all I need to tell you is, what are the widths of the stripes, and then I'd say, okay, they're all black and white, and the white stripes are this wide, and they start at this location, this location, this location. It's a very simple description, okay? I can probably send this message without too much information or too much communication. On the other hand, if this were just, scattered dots like all over the place, I would need to tell you the location of each and every single dot, right? And that has more information. So in a weird way, if you're watching digital TV and somebody's sending you a message which is a scene, okay, of some sitcom or something like that, that has less information content than just snow, when you have these dots all over the place, right? The dots all over the place is actually almost maximum information content, because I need to tell you exactly where every dot is, okay? So, of course, one could argue that you don't really care where the dots are, so I could just send you any information. I could send you any image with dots all over the place, and you couldn't tell the difference, so it has zero content. But anyway, from this perspective, if you do care about where every dot is, it has the most content. So the information content of a set of messages is precisely the entropy, and unlike the second law of thermodynamics, we don't have any such thing that says information content of a set of messages increases. We don't have that. It's just a word that we use over here. And the first thing that I've said so far is that h equals log n. Everything is base 2 here in this unless it's very rarely we'll use base 10, but basically everything is base 2. So if you have n equiprobable messages, I can tell you what the information content is. It says this, and because this corresponds to a path in a binary tree, okay? Now I give you a set of messages, okay? Message 1 to, let's say, message n, which are not equiprobable. They all have probabilities associated with them, and let's say this is probability p1 all the way up to pn. And I ask you, what is the information content? What's the entropy of this set of messages? The intuition that Shannon used was to say that the entropy, and he kind of defined this in this way, that entropy is proportional to 1 over likelihood. Okay. And the idea is that if a message is very likely, the recipient kind of already knew you're going to send that. Okay, but if the message is unlikely, if it got surprised, oh, I didn't expect that. And if it got an unexpected message, its information state went up higher. Okay, so as I say in the text, if you say, a dog bites a man, well, yeah, okay, fine, it's not news. But if a man bites a dog, okay, that's news. It's a low probability event, so your entropy goes up. Okay, which is why when you have a newspaper, they all have a section full of high entropy junk. A two-headed llama born in Peru, and dolphins like to brush their teeth. These are things that you never thought about. You actually don't even care about them, but these have high entropy. Okay, so they put it there because it sells newspapers. Okay, this is all kind of random junk. I mean, who cares? Two-headed llamas are born wherever they're born, but this is news. Okay, now from Shannon's perspective, these have high entropy. From my perspective, it's not particularly worth knowing. But at any rate, from the mathematical perspective, if this is a low probability event, so two-headed llama is a low probability event, we will say that it has a higher entropy. So how do we take it into account? What we do is we find that the average entropy is going to be given by the sum over the set of messages, pi log base 2 of pi, I is the messages. So what are we saying over here? This log base 2 pi is sort of the minus pi. So this one over here, the log of the message is sort of reminiscent of the log of the number of messages. Okay, and we are basically saying over here that the probability of the message in some sense corresponds to the number of messages. Okay, we're kind of taking individual message over here as opposed to the number of messages. So in the case where n equiprobable, what happens is log of n is the logarithm of the number of messages. We're not taking per message, right? Here we're taking per message, and again it turns out that mathematically we need to take the log of the probability, and then we're multiplying by sort of pi, because to get an average. Okay, so normally when you take an average, the average is basically x. So if you want to take the average of a distribution, we just say x times px. Okay, for xi pxi that's the average of the distribution over here. So maybe I should use the same terminology. Yeah, okay, this is fine. So this is the probability of the particular message, and that's the value itself. Okay, so if you want to take average of a discrete distribution, you take the value, multiply by its probability, sum it up, and that's the average value. Okay, over here what we're doing is this sort of is your xi, so to speak. Okay, is the log of the probability, because that's the likelihood. Okay, and we put a negative in front of it because that corresponds to log of 1 over pi. Okay, so I can rewrite this as sigma I p sub I log of 1 over pi. Okay, so what we're saying over here is that the more unlikely the message, the greater the value 1 over pi. Okay, and so the more the entropy associated with that particular message, and then on average it's going to be pi times whatever that value is. Okay, so this is the entropy is proportional 1 of likelihood over here, and so these two things mean the same thing. Okay, so the negative over here, we can view that technically as saying, well, this number is between 0 and 1, so the log is going to be negative, right? And so we want to make it positive, so we multiply by -1. But the intuitive way of understanding this is that we want to have something that is inversely proportional to the probability. So the more unlikely it is, the higher this value, and then that's a log we want to take of that. Okay, and then we multiply that by pi and sum it to give us the average, as we always do. We take the value. We take the value in its probability, multiply the two, we get this. And this definition of entropy, again, is Shannon's definition of entropy. And this is, you can choose to like it or not like it, but that's the way we define it. We have some intuition behind it. And it turns out that the rest of the math works very well when this is the definition. Now you could say, well, I don't like Shannon's entropy, I want my own entropy, and you can do that, but that would, you have completely different math after that. Yes, you had a question? No, okay. Yeah?
So is that the same H as before?
Yeah, it's the same H. Yeah, H is always entropy.
Yeah.
So we are defining H over here for equiprobable messages,
okay, and
this is H for non-equiprobable messages. And if the equiprobable, then we know, and we can actually show that they mean the same thing. That's one reason why that definition is kind of nice, is that if we substitute 1 over n for pi, okay, so if p sub I equals 1 over n, then H equals sigma, okay, 1 over n, right, log of 1 over n. Okay, and so this is a constant, so it's going to be n times minus, yeah, so it's going to be n times n over n minus n over n log of 1 over n, which turns out to be nothing more than log of n, right? So when it's equiprobable, this definition and that definition are the same, okay, when pi is 1 over n. Okay, so any questions about this so far? Okay, so now I'm going to take one step which is going to make life a lot easier for us, because so far I've been talking about messages and sets of messages and so on. And one of the first things we do in mathematizing it, of course, is to use this notion of a very limited notion of a communication. The second thing we do is that we say that the messages that are being sent are equivalent to a random variable. In other words, the probability, we can talk about the probability that the random variable x takes on the message. Okay, we'll call that p x, and the messages will be denoted as x sub I, p x equals xi, okay, or you can also call it p of xi. Okay, these all mean the same thing. So what we're saying is